Swayam Prabha. Digital India. Educated India.
Hello and welcome to lecture number 11 of the course Robot Motion Planning. In the last class, we looked at roadmap methods. That is, we make a set of pathways and then we connect the initial point to this network of paths and then find the most suitable path that will take the robot from the initial point to the goal point, avoiding obstacles. Today, we'll continue with that discussion and then move on to the next topic, which is cell decomposition methods. That is, how do you break the free space and the obstacle space into a number of cells, and then how do you find a path which will take you from the initial point to the goal point. Okay, today we'll be looking at cell decomposition methods, which is the next method after roadmap. So very quickly I'll complete a couple of points which are still left for the roadmap method and then move on to the next topic, which is cell decomposition methods. So in the last class we saw that roadmap methods basically captures the connectivity of free space by a graph or a network of paths. Like the example is Google Maps, okay, which everybody is familiar with these days, that if you want to go from some point to some other point, basically what it does is it finds a network of paths, okay, and then finds which is the shortest path in terms of distance and also maybe time, okay, to take you from one point where you are to the desired goal position. Similarly, if you look at this example in the right hand side where we have a workspace and there are obstacles, so CB1, CB2, CB3 are obstacles, and we have a robot at an initial point, and we want to go to the goal point, which is marked here. So what the roadmap method does is essentially it generates a network of paths, network of feasible paths. Feasible path means it should not go inside an obstacle, right? And then what it does, it connects the initial point to the network of paths and the goal point to that network, and then find different ways of going there. So this is the basic idea of roadmap methods. And from roadmap methods, what we do get is we can get the best path, which will take you from the initial point to the goal point, right? Now there are other methods also, like visibility graph is also a roadmap method, okay, in which we generate a set of pathways, and then we find the connection between the initial point and the path and the network of paths, or the goal point and the network of paths. And then as you can see here, there are multiple paths which can take the robot from the initial point to the goal point, and then we find which is the shortest length path, etc. Okay, so these are all called roadmap methods because they capture the connectivity of free space by a network of paths, by a network of feasible paths. Okay, and then they basically find the path which will take it from the initial point to the goal point. Visibility graph is another method in which you can imagine that you are standing at the initial point and which vertices are visible to you. You connect it with straight lines, and then all vertices are connected to the other vertices by straight lines, and then it's a question of going from one point to another point simply by finding the path which is the shortest length. For example, this one probably would be the shortest length path. Okay, now visibility graph also has a reduced visibility graph, something we looked at in the last class. So reduced visibility graph. Now in this reduced visibility graph, we basically remove the edges which are there in the concave parts to make it faster. Okay, so for this please refer to the previous lecture. Now the other method after this is, or rather the thought of the next method is that basically when human beings are going to avoid obstacles and go from one point to another point, we don't actually go very near the obstacle and almost go touching the obstacle, okay, and then try and go to the goal point like is being done here. Okay, so in this case, you're going from the initial point to the node, then you're going to the next node, and you're going to this node, and then you're going to the goal point. Now that is something which human beings do not do. Why? Because there is a chance of an accident because of wrong data, okay, wrong sensor data. So if the distance data from the robot and the obstacle is not very accurate, there is a chance the robot will hit the obstacle. Okay. Now to avoid that, what we do is we try and find a path which will go in between the obstacles like this, right? Keeping a safe distance between two obstacles. That is what we do, or any biological entity does. Now, the idea there is basically to find equidistance between obstacles and the workspace boundaries. For example, in this particular case, we are basically going to find equidistance relations between an edge and an edge. So you can guess that there are two obstacles like this. So this is one edge and this is another edge, one vertex and another vertex rather. Okay. Now what will be the equidistance path? The equidistance path will be something like this in between them. Now if on one side you have a flat straight line, other side you have a vertex like this, what will be the equidistance path? It will be something like this. Okay, how do we start? We basically start by finding the shortest distance here. So between this point and this point, that is the equidistant point. Then similarly between this point and this point, that is the equidistant point, and continue like that. Now if a surface has two edges like this, then the equidistant part will be in between. And this is basically the idea of deformation retracts, where we are trying to generate a Voronoi diagram that is going from the start to the goal point by using a network of paths which are equidistant from the obstacle and the workspace boundaries. So this is a network of paths, and how did we get them? They are basically equidistant. So this line here is equidistance between this and this. Okay. Now this here is equidistance between this side and this side. So now if you want to go from some point to some other point, basically what we do is we connect to this graph, follow a pathway, and suppose this is my goal, and I go from here and I simply go to the goal. Okay. So again you can see that this is a network of paths or pathways, feasible pathways. Okay. And the advantage of this is that it is safe. It doesn't go too near the obstacle, so there's no chance of hitting the obstacle or the wall. Now these are also called Voronoi diagram. This is also a Voronoi diagram, and this process is basically called deformation retract. It is like, say, it is like if this were to expand and this were to expand, they'll go and meet there. Okay. It's like both the sides are deforming and then they're going and meeting there. So similarly, if you look at a donut shaped object like this, if this one is shrinking and that one is expanding, where will it meet? It will meet in one dimensional circle like that. Okay. So this is basically what is called a deformation retract. Now there are other methods, fast methods by which you can make this deformation retract. Bushfire algorithm is one of them, where the object is marked as 1. Okay, the figure, the number 1, and then the adjoining cells. So this is basically a grid, kind of a grid workspace. And a computer can compute this very, very quickly. So this is given 1, 1, 1, 1, and the next grid to 1 is given 2, then 3 in that order. So you can see this is 2, then 3, 4 in that order. Similarly, from the work side, from the boundary of the workspace, we start with 1, this becomes 2, then 3. Now you can see that it can go maximum till 4, and then it starts meeting. Okay. So similarly, what happens is, if you look at this, so the one on the right side is showing the completed assignment of all the grid numbers. So whatever is the largest number that has been assigned, that is the one where the two sides are meeting. Okay, so for example here, this is the case where if you expand from here and you expand from here, this is what you'll get. So this is basically my deformation retract. But a computer would find this very easy to compute and do, because this is in a grid form and these are numbers. So it can do, you can write an algorithm very quickly to do this and find the deformation retract. Okay. Now if you are here, say I have initial point, you simply can connect to the node, and suppose you want to go here, this is my goal point, so you can simply follow this path like this and go there. Okay. So this is basically called the Bushfire algorithm. Now moving forward, we are looking at a torus. Now we saw that for a 2 degree of freedom serial arm, suppose we take this example, we did this a few classes back, where you have an arm, 2 degrees of freedom, and there is an obstacle. Now the C space for this would look something like as shown here in a torus. Okay. Now there's an obstacle there, so maybe part of the obstacle is going to come here on the surface of the torus now. Now I want to do path planning on this torus. Now please note that the torus is 2D basically. The torus has two variables, theta 1 and theta 2. But when you draw it, you require x, y, and z in terms of dimensions. Okay. So now if you want to do path planning, let's say this is my obstacle. I want to do path planning on the torus now. Now how do you do path planning on the torus? Okay. Now again we have eyes, so you can see very clearly. Suppose I want to go from here to here. Okay, so this is my initial point, this is my goal point. How do I go? Okay, so although we have eyes, we can see it's not very clear. How would you go? Would you go around like this? Would you go from under here? Okay, how would you go? And if you take the projection, it simply becomes a 2D, two ellipses, okay, which is of not much use. So this part is fully blocked if I take a 2D projection. Now, what about the back side? So if you want to go from here to here, do you go like this, or is there any other way? Now, to look at this kind of a problem, we move on to what is called the silhouette method. Okay. Now we're taking this example of the silhouette method using an ellipsoid kind of structure. So this is an ellipsoid. Okay, that means an ellipse in 3D. So it's an ellipsoid. Now this ellipsoid has a hole in there. Okay, so this is it's a cylindrical cut which is inside there. You can imagine that, I hope. Okay. Now I want to do on this particular surface, I want to do path planning. Suppose I want to go inside here. That's my goal point, and my initial point is here. Now how do I do? Now this is similar to this, that this is a torus, which is something like a 3D structure. Now this is also a 3D structure, which is an ellipsoid with a hole, and I want to do path planning here. Now in the silhouette method, what it basically does is we have the ellipsoid which is S, okay, with a hole. Now let us say that we have a hyperplane or a plane which is PC. This is a plane. Now we can call this a cutting plane, hyperplane or cutting plane. Okay. Now this cutting plane will slice this ellipsoid at various points, right? So let me draw my x-axis like this. This is my x-axis, that's my y-axis, and that's my z-axis. So this hyperplane is basically in the z and zy plane. Okay. Now in the x-axis, what I will do is I'm going to divide this x-axis into a number of points, and for each of these points I'm going to pass the plane. So when I pass the plane at 0, if this is my 0, then where does it cut the ellipse? It cuts the ellipse like this. Then next what I would do, I'll increment this x by 1 unit, it is 1. Okay, the plane is there now. Okay, so the plane comes here. Okay. Now you can see that it is going to cut the ellipse. Where is it going to cut the ellipse? It will cut the ellipse somewhere here like this, the red line. Okay, so we keep moving this hyperplane in this direction, and we keep taking slices. Okay, so this hyperplane is going to sweep through S in the x direction, and then at every slice, what we are going to do, we are going to see where is the boundary of that ellipse. Okay, so at each point the slice travels along the x, we will find the extrema points. What are the extrema points? They are basically the extrema points at these points. Okay, so we're going to get this curve, and what is the extrema point? The extrema point is this point and that point, okay, on the curve. So extremal points in y in the slice is given by this now. Okay, so this is my x-axis, y-axis, and this is my z-axis. So I took the slice. What I got is this curve by cutting the ellipse. Now in that, what I'm going to do, I'm going to take the extrema point, this point, and this point. Okay, and these are the extrema points in y in the slice S, that intersection PC. Okay, now if we trace these out, we get what is called the silhouette curve. So what am I doing? I'm going to cut this using slices, and every slice I find the extrema points, and in the extrema points what we do is we get our, so this is my these are the extrema points on the curve. Okay, now the observation that we need to observe here is that the silhouette curves are one-dimensional. Okay, now this is not a road map because they are not connected. Please note that these are not connected the way I drew it even here. So we get one curve here and we get another curve there. So these are not connected. So if I take the extrema points, one point is here, one point is here. Okay, but these are not connected. Now there are points where extrema disappears and reappears. These are called critical points. Now because the structure is such that there is a hole in there, so what will happen is there will be places where the extrema is going to disappear and reappear again. And these points are basically what we call critical points. Okay, so there are points where the extrema disappears and reappears, and these are called the critical points, and the slices that go through these points are called critical slices. Now a point on a silhouette curve is a critical point if the tangent to the curve at the point lies in PC. Now if you can imagine a little bit, what am I trying to do? Maybe if I want to do path planning, I want to go inside here. That's my goal. So basically, I need to find this point. I need to go inside that hole, right? The cylindrical hole. So I need to locate this point. And once I locate this point, then I can go inside. Okay. So what the critical points are doing is basically they're trying to locate where there is a change in the silhouette, in the curve, right? So in this slice, as you're going from here, what will happen is this is my critical point now. Okay. So we'll connect a critical point to the rest of the silhouette curves and a path that lies within SP. Okay. So now what we were doing till now is we were taking slices, and at every slice I'm going to get my critical points, which are here, which are here. Now the case where there is a critical point, what we do is for that particular slice, we connect the critical point with the silhouette curve here. Okay. So we'll connect a critical point to the rest of the silhouette curves with a path that lies in S intersection PC. Okay. So what we can do is, these are my silhouette curves. Okay, that's my silhouette curve, right? So what I do is, now I want to go inside the cylinder. So how do I go? I can go like this. Now this is the critical point. So I have to go like this, and then I can go inside. Okay, so I hope you can get the idea of why this critical point is important. Because in order to go inside, I need to find where is the critical point. And then once I get the critical point, now I know that I can go inside that hole now. Okay. Now, the recursion is repeated until there are no more critical points or the critical slice has dimension 1. The roadmap is the union of all the silhouette curves. Okay. So what we are getting is the roadmap is the union of all the silhouette curves. Okay. So now suppose I want to go from here to there. Okay. I have got my curves like this. Now these are my points on the silhouette curve. So what I do is I basically go like this. Now this is the critical point, so I can simply go like this. Now I can go inside there. Okay. So now we understand how to go inside this ellipsoid which had a cylinder inside by using the silhouette method. This is called the silhouette method. Now, now let's come back to where we started. That is the torus. Okay. Now, can I use the same method for the torus? Okay. Now, if I use the same method for the torus, what I'm basically going to do is I will have the hyperplane, the plane, which is cutting the torus like this. Okay. So if it cuts the torus, it will be cutting here. Okay. So I move this in this direction. Okay. If this is my x direction, that's my y direction, and that's my z direction. So in different intervals of x, I'm going to move this slicing plane, and at every point, I'm going to get the silhouette curve. Okay. This is the points where the curve is cutting. Okay. So there is one here, one there. So this is my silhouette curve, right? Now, if I take the projection of this, okay. Now what is going to happen at the critical values? Because at this point, you can see like there is a hole inside. Okay. So this is my critical point now. So in the slice through the critical values, you'll get one here, if you can imagine, and one here, like this. Okay. So when I cut using the plane here, what would happen is, here I'm going to get one curve only, it's continuous. But at that critical point, there'll be two curves now, one this side and one this side. If I take the projection on my XY plane, what I'll be getting is these two curves are getting projected here on this line. Okay. Right. That's what we have got now. Okay. So we were able to get the projection of the ellipse on this curve now. Okay. Now suppose I want to go from some point to some other point now. Okay. Now you can guess, I'm sure, that what is the use of doing this. Okay. Now suppose I want to go from this point to here. Okay. Or rather, if I'm here and I want to go here, this is my initial point, and this is my goal point. Okay. Now how do we go? So if this is my silhouette curve, the side boundary which I'm getting, these points I've got, right? So from here I can go like this, I can go like this, I can go like this, and I can go there. Okay. So this silhouette curve, okay, is actually giving me the path which I can follow. This is a type of a roadmap now. Okay. So I'm going to start from initial point, go like this, follow the curve here. Now that's a straight line which is having a critical point. Then I cross over here, I go like this, and I go there. Now if you simply look at the ellipse without doing this, it will be difficult to figure out how do you go? So what did I do? I went from somewhere here. I was here. I went somewhere here now. Okay. Without doing that, without doing this, it will be difficult to know how do you move on the surface of the ellipse. But once you do this, use the silhouette method, it becomes very clear that how you are going to go from one point to another point. Okay, on this torus. These are some more examples. Accessibility and departability. Okay, some examples here. So suppose you have an ellipsoid, again like this, and this as an obstacle. Okay. So what we do is basically I'm going to make my the hyperplane. I'm going to pass my hyperplane, and this hyperplane is going to touch it there, and this is my critical point now. Okay. So the first thing we do, we slice it and get our critical points. Now I've got my critical point here, 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 and here. Okay. And then what I do is suppose I want to go from S, which is my start point, to my goal point. I can draw another slice through here. Okay, and this is a path. It is giving me a path here. This is my path, and I can go to my goal point here, avoiding this, and this. Okay. Now I hope you understand. How this method works. That by simply slicing this, what we are doing is we are getting a series of connected paths, which is taking me from the start point to the goal point. And this method is called the silhouette method. Okay. Now, so much for roadmaps. Roadmaps are basically generating a network of pathways. Okay. Now, the next method is basically called cell decomposition method. Now, as the name indicates, the cell decomposition method basically decomposes the cell, the workspace, into a number of cells. Okay. And there are different methods which are used here. Number one is polygonal cell decomposition. Second is trapezoidal cell decomposition. Then we have the Moose cell decomposition. Okay. Then we have this Bostrop-Ponden cell decomposition. Then we have Moose decomposition and sensor-based coverage. Okay. These are more or less used for exploration. So exploration is one, coverage is the other. Okay. So the point is not only that, suppose I have a work cell and I have an obstacle here. Okay. The robot has to go from here to here. That's just one problem. Now it could be such that the robot actually has to explore everywhere and not simply go from one point to another point. Okay. Suppose it is mapping the area. The other is coverage. Suppose there is a vacuum cleaner which is cleaning this room. Suppose this is a room and this is a table. Then it has to cover all the points. Okay, that means it should not leave any point uncleaned. So that is where basically these coverage algorithms come inside, and these three are basically coverage algorithms. How the robot can cover all points, not only avoid obstacles. So let's start off with the first one, which is polygonal cell decomposition. Now, as the name indicates, the polygonal cell decomposition basically works like this. So a convex polygonal cell decomposition is a finite collection of convex polygons called cells, such that the interior of any two cells do not intersect and the union is equal to the free space. Okay. Now what this means is that this is my workspace. Okay, and these are the vertices there. Okay, and these are my obstacles in here. So this one is also a green obstacle. Okay, so this one is also a green obstacle. Now, convex polygon decomposes this total workspace into a number of cells, okay, by a finite collection of polygons, such that the interior of any two cells do not intersect and the union is free space. So let us start off by how this proceeds. Is let us connect, okay, all these vertices to the vertices of the object. So there is one here, there is one there, one here, okay, then there is one here, okay, there is one here. Okay, then this vertex is coming here, this one is coming here, it's coming here. I'm just connecting all the convex vertices. Please note that they are convex polygons. Okay, so the other connection we are making is here, here. Okay, then we are making a connection here, here. Okay, so these are all connections. I'm connecting the vertices. Okay, I've made my connections. Okay, So I have divided the whole workspace into a connection of cells, okay, by connecting the nodes and the vertices. Okay. Now what we can do is we can number the cells. We can number the cells. Let's number the cells. This is 1, this is 1, this is 2, this is 3, this is 4, this is 5, then this is 6, that one is 7, okay, 8, that is 8, this is 9, okay, let's say this is 10, 11, 12, 13, 14 and 15. Calculated, I have connected all the cells. Now if I want to make a connection diagram now, what is the objective? The objective is to take the robot from some initial point to some goal point. Okay, so what I can do is I can make a connection diagram now. 1 is connected to 2, 2 is connected to 3, 3 is connected to 4, 4 is connected to 7, 4 is also connected to 5, okay, 7 is connected to 8, 8 is connected to 9, 9 is connected to 10. Now 5 is also connected to 6, 6 is connected to 11, 11 is connected to 10. Now 1 is also connected to 15 and 14, okay, right? So we have got our, there is a connection here also, one here and one here, okay. So these are all the connections in between the cells, right? So I've connected, I've put numbers onto all the cells and I've connected the cells. Okay. Now I know exactly what the connection diagram would look like. In fact, this red line is showing you the connection diagram. So if you want to go from cell number 1 to cell number 11, how would you go? So you can choose two ways. You go to 1, 2, 3, 4, 5, 6 and 11, or you go for 1, 15, 14, 13, 6 and 11. Okay, there is a third path also, 1, 15, 14, 12, 10, 11. Okay, so this is basically giving us a, I have divided the total workspace into convex polygons called cells, and I can find connections, okay, between cells now. Okay, so I have done my connections, and this is my connections between the cells. Okay, now once we have got the connections between the cells, now suppose I want to find the path. So these are the connections, red line. Okay, now I want to find a path to take me from one point to another point. Okay, so how do I do that? Now that's very simple and very interesting, in the sense that if you look at this now which will be the path? Now what I do is I take the mid, suppose I have I want to go from my initial point here. Okay, this is my initial point. Okay, and this is my goal point. Let's say goal point is right here. And that's my goal. Okay, so from initial to goal, I see that I can go from 1, 2, okay, then 3, then 4, then 7, 4, 7, 8, okay, and then it's a 9. Okay, that's the path. Okay, this is the different cells that are there, right, to take me from the start point to the goal point. But now what I can do is I can very cleverly take the midpoints of the path, midpoints of the sides, of the edges. So I take the midpoint here, midpoint here, midpoint here, midpoint here, midpoint here, midpoint here. Okay, and I simply connect it. This one, this one, this one, this one, this one, this one, this one. I've got gone to my goal. Okay, so first what I do is I make my connections. Okay, then I take the midpoints, midpoints of the edges, and connect them by straight lines, and that is how we get our how to go from one point to another point. Okay, this is called polygonal cell decomposition, because we are dividing the total workspace into a number of convex polygons, and then I number the different cells, find the connection between the cells, and to find the path I simply take the midpoint of the edges which are making up the polygon. Okay, and I simply connect it and I get my path. Okay, now a computer can do this very quickly, and this method is called the polygonal cell decomposition. Now the other method in cell decomposition is trapezoidal cell decomposition. In the case of trapezoidal cell decomposition, as the name indicates, and you would be guessing by now, so we are going to divide it into a number of cells. Okay, so the free workspace is divided into 2D cells that look like trapezoids. And so the input to the algorithm is the vertices of workspace coordinates and vertices of obstacle coordinates. So this is my coordinates of the vertices of the workspace, and these are coordinates of the vertices of the object, right? So this is the input to the algorithm. Now what the algorithm basically does is it has to divide this into a number of cells. In the previous case it was polygonal cells, here it is trapezoidal cells. Now, how it does that is it takes every vertex and draws a straight line. So from this vertex it is going to come down here. Okay, in this vertex is going to go up, this vertex will come down, this vertex will come here, and up there, this vertex will go there. Okay, so I hope you can see what is going on. So what is going on is that we are dividing this into a number of cells. Okay, once I have divided this into a number of cells, then what I'm going to do is I'm going to number them just like before. So 1, 2, 3 in that order. Okay, and go on and then find the connection between the cells. And once you have found the connection between the cells, how do you find the path? You simply see the connection of the cells to form the path and take the midpoints of those straight lines, and then you have your path. Okay, so let's see how this is done. So how this is done is in this particular case we have seen that so the path planning is done in 2 steps. The path planner determines cells that connects the start and the goal. Then the planner searches for a path within the adjacency graph. Okay, let's see how it is done. Okay, so at each of these vertices, okay, what we are going to do is we are going to draw straight lines. Okay. Now at each vertex, draw line segments, one going up and the other going down. Lines do not go through obstacles. Okay, I'll just explain. So what we are going to do at a vertex is I'm going to draw a vertex like this down, and from here I'm going to draw it up. It will not go through obstacles. Okay, it should not go through obstacles. Okay, now wherever there is an edge like this, in this particular case it is going to go up and down at every vertex. So in this vertex we are going to draw a line up but not down because it is going through an obstacle. Okay, in this vertex you are going to draw a line down but it doesn't go through an obstacle. Okay, so this is what we are going to do and divide this into a number of cells. Now once you have divided this into a number of cells, I am going to number the cells 1, 2, 4, 5 in this way. Okay, so each cell has been given a number. Okay, now we know the connection between the numbers. Okay, so for example, C is connected to 2, 3, 4, 5. 5 is connected to 8. This is connected to 10. 10 is connected to 11. This is one. This is another one. Okay, and there is another one going on top. This is connected. That is connected. That is connected. This is connected. This is connected, and this one is also connected. Okay, so now I know which cells are connected to which cells. And now if I want to find a path, what I do, I simply take the midpoints of those lines and I simply connect it. Now that's the path which is going to be equidistant from the obstacle and the workspace, and that is going to give me a connected graph now. Now how do we run the algorithm? Now in path planning or motion planning, we are worrying about algorithms. Now algorithms basically means a program, right? Now this program has to automatically decide. Now we have eyes, so you can see, I've said this many times I guess, that we have eyes, so it is very easy for us to see, okay, suppose you want to go from here to here, okay, there is a path like this, like this, like this. But the poor robot doesn't have eyes, okay, and the program doesn't have eyes, of course. So how will it basically divide these cells? So what we do is we start off with a straight line. Okay, so we start off with a straight line, okay, and sweep the straight line. So this is basically sweeping sometime back. We had also looked at the sweep line algorithm, okay, in the case of the Voronoi diagram. Now here also we have a straight line like this which we are sweeping. Okay, now as we are moving, whenever the straight line hits the vertex, now geometrically we know the equation of the straight line, we can find out if the vertex is lying on the straight line. Okay. So the moment it hits the straight line, we know that's a vertex and it's a line which is going up, which is going down. So I move the line a little bit more on the right until so I'm sweeping this line in this direction. The moment it hits that, I know it's hitting a vertex, and then I take it up and I take it down. Now I know it's hitting here and it's hitting there. So that's my first cell. I'll repeat it. So there is a straight line which is being swept in this direction. Okay. So here when it is hitting the vertex, I know this line is going up and this line is coming down. Okay. So it is the straight line. So I get this point, I get this point, I get this point. Now I sweep it more this side. Okay. What happens? It hits, I get this one. Okay. Now it should not go through an obstacle, so it does not go through an obstacle, right? It just ends there. Then I get this one. Okay, then the sweep line gets this one. Okay, on top it gets that one. Okay. So in this way, what it is doing is it is sweeping through the space. The straight line is sweeping through the space, and we are getting this connected graph. Okay. So then what we do is we draw this connected graph of cells. Okay, so this is 1, 2, 3, 4. We can see that this is one connected 1, 2, 3, 4, then 7, 14. This is one branch 7, 14, 15. Now from 5, 8, 10, 11, 5, 8, 10, 11 is one branch. Okay, and the other branch is coming this side, C3, 6, 9, 10, 11. 6, 9, 10, 11. Okay, and from this side it is coming to 13, 14, 12, 10. 13, 14, 12, 10. Okay, so what we are seeing is we are getting the connection between the different cells. The connected graph of cells. Now suppose I want to go from some point to some other point. Okay, what we need to do is I simply need to join the midpoints. Okay, as usual, from the connected graph. Suppose I want to go from the one point to another point. Let's have a look at this. I want to go from the start point to the goal point. What I will do is I will look at C1. The start point is in C1, so it is in C1. The goal point is in C15. It's in C15. Okay. Now I know which is the path. So this is the path. Okay. Path in terms of the cells. Now how do I get the path actually in terms of points? What I do, I take the midpoints of these lines. So I take midpoint here, midpoints of these straight lines. Okay. And I simply connect it like this. And that is going to give me the path which will take it from the start point to the goal point. Okay. Now the algorithm is basically using the sweep line method. Okay, and the ultimate goal of the sweep line method is to divide it into trapezoidal cells, and then once we get the trapezoidal cell, the lengths of the straight lines, then we can find the midpoint. Okay, now the sweep line, it sweeps through the free space, stopping at the vertices. So we sweep the straight line. This is my straight line. So I start off here. I sweep it until it hits a vertex. The moment it hits a vertex, it goes up or down depending on whether it's going through an obstacle or not going through an obstacle. So if it is going through an obstacle, it doesn't go anymore, it stops there. Okay. The next is, as we are going, we have to maintain a list of all current edges and slices intersects, and we keep updating that main list depending on the way the upper lines are intersecting. Now, depending whether the vertical lines are above, below, or through the obstacle, decide on the midpoint of the segments. Okay, this is basically the working of the algorithm. So basically what it is doing, this is a straight line. Okay, so it is starting. So what it is doing is we have got the straight line hitting the vertex consisting of E8 and E13. So E8 is here and E13 is here. So what we have done in terms of the algorithm is that we have noted the vertices, okay, plus the edges which are marked. Then we are going to maintain this set. It starts sweeping, and here it is E8 and E13. Okay, so E8 and E13 is the first vertex here. The next, it goes a little bit more right. What happens? It hits this one. Okay, so it hits E8, E0, E3, and E13. Okay, so it sweeps a little bit more. You can see it is hitting now E8, E0, E3, and E13. Now, when it is hitting the vertex, we also check if it is going through an edge. If it is going through E3 like this, okay, then we discard the upper part. Similarly, from the top, when it is coming down, hitting an edge, then is it going through the edge? Okay, that we can check very easily. And then we discard that part. We just stop it there. Okay, so we keep updating this list as the line is sweeping, and then finally we come up with the total list of vertices and the lengths of the line which are going there. Okay, so after doing that, what we get is the final list that will come out will only consist of the lines, the length of the lines which are being drawn. So for this one, we'll have the full one. This will have only from here to here. This will have from here to here. Okay, that is how we are maintaining our list. Now, this is basically to show or to find a path from an initial point to a final point by a connected set of roads. And this method is called the cell decomposition method because we are breaking it up into cells. Now, path planning is not just about finding a path. If, for example, as I said, that we have a workspace and an obstacle space, and I want to go from this point to this point. Okay, so one point is one of the applications is just to find a path, avoiding obstacles. Okay, but there are other requirements for covering or exploring the full workspace. Exploration means, suppose the robot doesn't know that there is an obstacle here. Where is the obstacle? It has to explore this area and find out where are the obstacles, where are the paths. Other applications are places like demining. These are defense applications where the mines are laid in particular ways, and the robot has to actually find out these mines. Okay. So this robot, in order to do that, the robot has to cover all the space. It cannot leave any space. The third is very common these days is cleaning. So automatic vacuum cleaners, for example. So automatic vacuum cleaner. Okay. So automatic vacuum cleaner is supposed to vacuum clean. Let's say I have a room like this and I have a table, and the vacuum cleaner is supposed to clean everywhere. So the question that is being asked here is, it is not a question of going from one point to another point. It is a question that I have to cover. Now, how do I cover? Do I go like this? Do I go there? Do I go here? And do I come back like this? Is that a better way? By covering everything and not leaving any part? Okay. Or should I take some other path? Should I do this part first, then I do this part, then I do this part, then I do this part? Okay. How does it guarantee that I've covered everything and I have not missed out any part? That is the meaning of what we call exploration and coverage algorithms. So exploration and coverage algorithms. Okay. So the basic idea of coverage is that the planner determines an exhaustive walk through adjacency graph. Now, these adjacency graphs are basically cells which are connected. Okay, so connected cells. Now, the planner computes explicit robot motions within each cell. And in this particular case, exact information is required. For example, we have a workspace. This is my workspace. And this is my obstacle. Okay, I want to clean the full area, or I want to cover all the area. Okay, or I want to perform what is called an exhaustive walk. That means I want to go everywhere in this cell. So what we can do is we can break it up into cells or adjacency graph. So I have broken it up into cells, like in the previous case, trapezoidal cell decomposition. And then I start cleaning each of the cells one at a time. That will ensure that I have covered all the cells and there is no cell which is left. Okay. Now, how do we do that? So this is called Bootstrap decomposition. The disadvantage of this trapezoidal decomposition is that there are too many small cells that are formed. So whenever we looked at this trapezoidal cell decomposition, we saw that, let's just go back to this figure. Yeah, here. So you can see that there are so many cells which are being formed here. Okay. Now, if you start cleaning one cell here, there are too many cells, and it gets, in a way, it gets a little confusing. Okay. So if you want to simplify it, what is done here basically is that only vertical lines that can be extended up or down the vertices are considered. Okay. Such vertical lines are called critical verticals, and the rest of the lines, other lines are ignored or erased. Okay. So the lines which can only go up and down from a vertex is kept. The other lines are all deleted. So from this vertex you can see that this line can go right up and right down. There is no vertex here, so this two can go, so this is not required. Similarly, this one can go up but cannot go down, so this is also gone. Okay. Now this one, the line can go up and the line can go down. Here the line can go up and the line can go down, so this is kept. This is deleted, this is deleted. So what you get is this now. This is a much more clean Okay, this is a clean space. Okay, this is a better representation. Now, if I want to do path planning, sorry, not path planning, I want to do the coverage algorithm basically. So, what I can do is I need to find the connection between the cells. Okay, so I have found the connection between, let me go back to the previous one. I can find the connection between the cells, let's say 1, 2, 3, 4. Okay, and then there is one more which is 5. So, there are actually only 5 cells. Okay. Whereas if I had done the previous case, that is this case, how many cells would there be? So there will be 1, 2, 3, 4, 5, 6, like that. Okay, so here actually there is only 5 cells. So I have a connection only between 1, 2, 3, 4. Okay, and 1 comes here, 5, and that goes there. That's enough. So if I want to now move the robot to clean each cell, I can go from 1 to 2, 2 to 3, 3 to 4, 4 to 5, and my job is done. Okay, so I hope you understand how this is useful for a coverage algorithm, where the robot has actually covered all the area, which has not left anything. Okay. Now, this is another example where we are dividing it into a number of cells, and the exhaustive walk is following this cell 1, 2, 4, 2, 3. That is 1, 2, 4. So it is going from 1 to 2, then to 4. Then it is going from 4, it is going to 2, back, and then it's going to 3. Then 5, 6, it's going to 5, 6. Then it goes back to 5 again, then it goes to 7, then it goes to 8. Sorry, 7 to 5, then to 8, 8, and then back to 1. As you can see that there could be more than one way of doing this. Okay, so which is the most efficient and the optimal way? That is an interesting question. That in this particular case, suppose we are going like this or we're going like this, which would be faster? In this particular case, it's a simple case. There is only one loop. Okay, whereas in this case, there are 2 loops. Okay, there are loops in here. So which would be, and there is a dead end here, 2 of them there. Okay, so if you go into 6, you have to come back this way. So this is an interesting question of this coverage algorithms. Now, something that you would have noticed here is that when I said that I have to cover this, which is okay, but then how do I cover it? What kind of motion do I have in one cell? Let me consider this cell. Will the robot move like this? Okay, it has to cover every point, remember. Okay, or should it start going around like that? Okay, which is a better way of covering it? That's an interesting question. Well, there are different ways by which you can do. For example, Morse decomposition is one way of dividing the cells. Okay, so you have this number of connected cells. Okay, so what I do is basically we look at the critical points, that is the points at which the line is going to hit or change direction. Okay, and then I divide it into a number of cells. So I have changed this into a number of cells. So connectivity of the slice in the free space changes at the critical point, that we know. And what we have done is, these are my cells. Now each cell can be covered by back and forth motions. So it simply does this and covers it out. Okay. Now let's see this further. So incremental construction, how do we construct it? So basically when we are constructing it, we are starting with a straight line. Okay, and the straight line is sweeping from the left side, as you can see, and every time it gets a critical point, it forms this it forms the next cell. Okay, finally we have from here we go here, the line is sweeping towards the right, here, and we have covered all the cells. Okay, now how do we detect the critical points? So you can detect the critical points like in the previous case, wherever it is hitting a vertex or there is a change in gradient of the surface profile there, then is the line going up and also down? Okay, that point will be a critical point here. Now, Morse decomposition in the previous case was being done by using a straight line. Okay, so what is the difference between that? So what is the difference between what we had just done in the cell decomposition here? Okay, between here and the Morse way of doing things. Okay, so what is there? You see that this is a complete cover here. Yeah, this is what I was talking about. So here, what we are doing is basically we are dividing it by straight lines, and then we are having motion like this. But in the Morse case, we can divide it by not by straight lines, only by straight lines, but we can divide it by other kind of curves also. Now let's see what happens if you start using this kind of a Morse decomposition, where you are dividing this by using this arcs. So we start from here and draw circles, x squared plus y squared. It's like the circle is increasing. So we have a circle here. Now the circle increases, has one point there. Then the circle increases further, it has one more critical point there. It increases further, has a critical point there. So in the previous case, it was straight lines which was moving. Now it is circles which are moving. Okay, so the circle is simply increasing and it is hitting at this point, this point, this point. These are my critical points now. Okay, and now we have got different cells like before, 1, 2, 3, 4, 5, 6, 7. And I can do the same thing to do the coverage algorithm. So because they are circular, my motion is circular now. The robot is cleaning like this, then it goes like this. Okay. Now I can do it in some other way also. Say for example, we can do mod of x plus mod of y. In this particular case, I'm dividing my cell into this rectangular fashion. And the robot is moving like this now, if you can see. Okay. So it comes here, does this, then goes there. So these are all ways by which you can do efficient planning. So it's an interesting question whether using the straight line would have been faster or the circle would have been faster. It depends on the geometry. Okay, it's difficult to say. So you actually have to see which one will give you the better. Now you can also use a tangent, tan of y by x. So from this point, straight lines are going off tangent to the curves here. And these are my different cells. So it's my 1, 2, 3, 4 like that. And my coverage algorithm also is going to take, is going to move this way. Okay. Okay, so it will move like this. So these are different ways of dividing the cell. They're all cell decompositions, different ways. Bushfire algorithm is another way. Now this bushfire algorithm is very interesting because we are dealing with grids. Okay, now in grids, you know that in a computer, if you can divide this, your workspace into grids and assign numbers, then the computer works very, very fast. It can do it very easily. Okay, as compared to putting concave and concave objects, finding the vertices, finding the intersections. Whereas in this case, what we do in the bushfire algorithm is basically we assign this as 1, okay, and the next grid will be assigned 2, then it will be assigned 3 in that way. So this is 1, 1, 1, this is 2, 2, 2, this is my 3. So basically what I'm going to get these curves. Okay. So the objective is to be able to break the free space into a number of cells. And these are also called free cells or Voronoi regions using bushfire algorithm. Okay. Bushfire algorithm I just explained in the beginning of the class today. Okay. That if there is an obstacle here like this, I name this as 1. I name this as 1. The second one will become 2. The third one will become 3 in that order. And wherever the highest numbers meet, that's your region. Now from here what we can see is that we have divided the full space into a number of points. And so this is my first point, second stage, third stage, and fourth stage. So how many cells are there? So we can see that these are 1, 2, 3, and 4 cells, and the black one is the obstacle cell. So I have basically got, using cell decomposition, I have got 4 cells. Now I can clean each of the cells one at a time. So the robot has, the coverage algorithm basically starts performing an exhaustive walk on each of the cells one at a time. Okay. So today we looked at, we started off with roadmap method. We just completed the silhouette method. Okay, that is, we pass the hyperplane, get the silhouette curve, and see how to complete the roadmap to take the robot from some point to some other point. Okay. Then after that, we looked at cell decomposition. Cell decomposition is, we looked at polygonal cell decomposition, then we looked at trapezoidal cell decomposition, then we look at the coverage algorithms. So these are all algorithms which are used for the robot to go from one point to another point or for coverage. Okay. Now what you would notice here is that this is basically a geometrical problem. Okay, and what is the input to the algorithm or the program is the geometry of the workspace. That means the coordinates of the vertices of the workspace and the vertices of the obstacles. Okay, now so this gives you some idea that when you write a program for either a simulation or in the case of a real robot, which is going to go from some point to some other point, how the program is written and what is the output, what is the input of the program, okay, and what is the output of the program and how it works. So today we'll stop here, and next class we'll move on to the next set of methods. Thank you.